This is the second video on the graphs of functions, their first derivatives and their second derivatives. If you haven't watched the first video, that's okay. This is a completely separate topic. In this video, you're going to learn how to find and justify concavity of functions. That's also related to finding points of inflection. One thing I've noticed over the years in my calculus classes is the students will misuse one of these words, positive and increasing, because they often use them interchangeably. But that's not true. Imagine a function. Well, don't imagine, just watch my function. Let's name this function f. So we could ask two questions. Where is f positive? And when we look at the graph, f is going to be positive everywhere to the left of this x-intercept. Positive means the opposite of negative. Positive means to be greater than 0. So where f is positive is where this graph is above the x-axis. Does that mean the same thing as increasing? It doesn't. In fact, if I asked you where is f increasing, you'd say nowhere. Increasing means to get larger, or with a larger x value, the new y value is larger. F is clearly decreasing everywhere. So watch out for the difference between positive and increasing. Well, concavity is about a change in a derivative. Let's see if we can get a visual example of that. So an increasing first derivative, well, first derivative tells us the slope of a function. So what would that look like if the slope of a function was increasing? The slope of a function is growing. Well, let's start out with a slope of 0. Imagine a little tangent line. A slope of a half, a slope of 1, a slope of 2, a slope of 3, a slope of 4. Could you imagine a function that has tangent slopes like that? I'm sure you're thinking, ooh, a parabola. Yeah, that will work. So this part of a parabola has an increasing first derivative. Why am I saying that? I'm going to write some numerical values. Here, a slope was 0, slope of 1, slope of 2, slope of 3, slope of 4. As we choose points to the right, meaning the x's increase, the slopes grow larger. So the first derivative of this yellow graph is increasing. What if I draw the other half of this U-shaped function? Is the first derivative of this graph increasing everywhere or just on the right-hand side? Well, let's draw some more tangent lines and make up some numbers. So maybe this slope is -4, -3, -2, -1, 0. Okay, are those slopes -4, -3, -2, -1 increasing? They are. They're getting closer to 0, but if you think of a number line, when you increase -4, that becomes -3. Hopefully that works for you. So we're going to do some vocabulary here in a second, but an increasing first derivative, well, increasing means a positive rate of change. So we could say that an increasing first derivative indicates a positive rate of change of the first derivative. Okay. And so a rate of change is a derivative phrase and then first derivative. So a graph like this that has an increasing first derivative has a positive second derivative. Right? And we have a name for that. Okay? So let's say that again. An increasing first derivative indicates a positive second derivative. Okay? So that's what we had back here. An increasing first derivative indicates a positive second derivative. The analogy there is the positive slope of a function indicates a positive first derivative. Let's think about that. So e to the x has a positive slope everywhere. And how do we know that? Because the first derivative of e to the x is positive. Okay, so that shape you saw before, imagine something that could catch water falling from above, is called concave up. That is where the second derivative, so let's say y double prime, is positive. The slopes as we move from left to right are increasing. Concave down would look something like this. When a graph is concave down, the second derivative of that graph is negative. Let's see if we can think about why. What if I draw little tangent slopes on here? That slope would be a large positive number, a smaller positive number, a slope of 0, a negative number, a larger negative number. As we choose points from left to right, the rate of change of y prime is negative. And we know rate of change is derivative, so it's the derivative of y is negative. So y double prime is negative. Okay, is it possible for a function to be both concave up and concave down? For sure. Okay, so if we drew a graph like this, this graph is sometimes concave up and sometimes concave down. Let's see if you can figure out where this graph is concave up. It's concave up right about in here. I'll trace over that part. Where is this graph concave down? This graph is concave down everywhere else. Okay. And so what do you suppose these two places are where this graph changes concavity from concave up to concave down, or concave down to concave up? They're points of inflection. So I do want to make one small point, and that is using the graph 1 over x. Okay, so 1 over x is concave, is that up or down to the right of 0? Concave up when x is greater than 0, and 1 over x is concave down when x is less than 0. So where is the point of inflection for 1 over x? Well, the only place I suppose would be at 0, but 1 over x is undefined at 0. So even though the concavity of 1 over x changes, 1 over x doesn't have a point of inflection. You need to make sure for almost everything that the function you're talking about is continuous, or at least know where that function is discontinuous. So let's break this apart. We know what x squared looks like. Something like this. And where is x squared concave up? Well, we kind of know our answer already. Well, x squared appears to be concave up everywhere. But because we have to justify, we're going to need some calculus. Is concavity about y prime, or y double prime? It's about y double prime. Now, start off in a super shocking way. X squared is a polynomial. So, x squared is continuous and differentiable everywhere. That's gonna help us out. Okay. So what do? Well, we're gonna find y double prime. That shouldn't take us too long. Y prime is 2x. Y double prime is 2. And then we need to find critical values. Where is y double prime equal to 0? Y double prime is never equal to 0. And y double prime is always defined. I think you knew that, but I just feel the need to say it. So let's make a sign chart. These are x values, and we're going to find the sign of y double prime. Let's put all our critical values on this sign chart. There aren't any, which means the sign of y double prime can never change. Y double prime is equal to 2, which is always positive. Okay, so I think we're ready to write our answer. Let's get another color to make that pop. Y equals x squared is continuous. Y double prime is greater than 0 everywhere, or always. So, y equals x squared. Oh no! So y equals x squared is concave up everywhere. Now you could also delete those everywheres and what we would have would still be true. Because when you say y double prime is greater than 0, without saying everywhere, you actually do mean everywhere. Okay, let's think about the graph of e to the power x. And we're looking for where e to the x is concave down. Well, it doesn't appear e to the x is concave down anywhere. It appears e to the x is concave up everywhere. So let's see what we get. Well, we know what e to the x looks like, and e to the x is continuous everywhere. We never want to forget to write that. Okay. And concavity is about a second derivative. The first derivative of e to the x is e to the x times the natural log of e. And the second derivative of e to the x is again e to the x natural log of e. Okay, well, let's see what we get. Maybe we let y double prime equal 0. So where is 0 equal to e to the x? Well, look at the graph in the top left-hand corner here. Where does this graph cross the x-axis? It does not. Okay, where is e to the x undefined? Also not. In fact, so that's interesting. We sort of already said that. Maybe we should say y double prime e to the x is always defined. Earlier we said e to the x is continuous, which means the derivative e to the x is also continuous, but weirdly the one e to the x is different than the other e to the x. Okay. What does that mean about the sign chart we're going to create? Well, without any critical values, y double prime can't change sign. So choose any number you want, put it into e to the x, y double prime is e to the x, and you get a positive number. Well, what does that mean about where e to the x is concave down? Well, that's pretty easy. E to the x is concave down when its second derivative is negative. So what are we going to say? Y equals e to the x is continuous everywhere. Since y double prime is greater than 0 everywhere, y equals e to the x is never concave down. All right, let's try to put all of that together. So what do you suppose x cubed minus 9x looks like? Well, maybe we can factor. So we can factor out an x, and you'd be left with x squared minus 9, so x minus 3 times x plus 3. So a 0 at 0, a 0 at 3, and a 0 at negative 3. Hopefully you know that x cubed minus 9x is odd, so we're going to see symmetry about the origin. Or you can imagine I drew that neatly. Y equals x cubed minus 9x. Okay. So we're going to do this visually, and then in a moment we're going to do all of that stuff algebraically. But I want you to be able to see on a graph. Let's answer this first part. Well, just visually, where does it appear x cubed minus 9x is concave up? And let's use the word appears. We don't have any proof. So y equals x cubed minus 9x appears to be concave up. Let's figure out an interval. On the open interval, starting at 0 and going on to infinity. We're looking for this upward facing shape that like could catch rain or something like that. That's the way my calculus teacher told me. Okay? So thing 2, where is x cubed minus 9x concave down? Again, we're just doing this visually. X cubed minus 9x appears to be concave down. And we're looking for this shape. From negative infinity up to 0. Ooh, what about a point of inflection? Well, by that, a point of inflection is where the concavity of a graph changes at a point. So x cubed minus 9x appears to have a point of inflection at x equals 0. And I suppose the point is 0, 0. We do know that. All right, let's do the algebra to prove what we see or to confirm what we think. So whether we're talking about concavity or points of inflection, that's about the second derivative. Okay? So what are we going to do first? Surprisingly not second derivative stuff. We're going to say y equals x cubed minus 9x is continuous, and we know that because x cubed minus 9x is a polynomial. Okay, so now we can say y prime is equal to 3x squared minus 9. We don't need to worry about anything with y prime because we're worried about concavity and points of inflection. So we find y double prime, which is 6x. Okay, so we're going to let y double prime equals 0, and we know y double prime is always defined, so we don't need to write that. And we get x equals 0 is the only critical value. That's the only place that y double prime can change signs. And actually, we kind of knew that already. Now we have proof. Okay. Well, we don't have a ton of proof yet. What am I going to do next? Let's make a sign chart. Arrows at the end because the domain we're given is all real numbers. X equals 0. Yep, these are x values. And now, the sign of not y prime, y double prime. So let's choose a number greater than 0 like 1. What do you get when you put 1 into 6x? A positive number, which means y is concave up for x values greater than 0. Choose a value less than 0 like negative 3. When you put negative 3 into y double prime, you get a negative value, meaning y is concave down for x values less than 0. Doesn't that look like what we graphed earlier, x cubed minus 9x? Okay, now we are ready to write our justification. What color do you think we should use? Well, if you said red, my computer disagrees. Okay, so what do we start off with? Y equals the most important thing, x cubed minus 9x is continuous. And we want concavity and points of inflection. So what do you want to do first? Okay. Y equals x cubed minus 9x is concave up. And you give us the interval from 0 to infinity because y double prime is greater than 0 on that same interval, 0 to infinity. Let's get rid of that period. And is concave down on negative infinity to 0 because y double prime is less than 0 on negative infinity to 0. So that's our justification of the concavity. Okay, let's worry about points of inflection now. How many points of inflection does x cubed minus 9x have? Just one at x equals 0. That's where the concavity changed. But realize we were asked for a point, which means we need the y value as well. So maybe we should put that work in. So using x equals 0, y is equal to 0 cubed minus 9 times 0. Okay, so we're talking about the ordered pair 0, 0. So at x equals 0, y double prime changes sign. So y equals x cubed minus 9x has a point of inflection at that same spot at x equals 0. The point is the ordered pairs 0, 0. Maybe the point of inflection. Maybe we should write that. All right. That should be enough for you to go on.